Welcome, fellow developers and tech enthusiasts. Today, we're diving into a topic that's quickly becoming crucial for modern software development: accelerating Java microservice deployment using the power of AI-driven Dockerization. If you've ever wrestled with bloated Docker images, slow build times, or security concerns in your Java applications, you know the pain. Manually crafting an optimal Docker file for every microservice can be a time-consuming and error-prone process. It demands deep knowledge of Docker best practices, JVM nuances, and security considerations, all while trying to keep up with evolving standards. This often leads to developers taking shortcuts, using generic Docker files that aren't optimized for specific applications, resulting in larger image sizes, slower deployments, and potential vulnerabilities. Our goal is to show you how generative AI tools can revolutionize this by recommending and generating highly optimized Docker files, drastically cutting down on manual effort and improving your deployment pipeline. Imagine a world where your Java microservices are deployed faster, more securely, and with minimal human intervention. This isn't science fiction, it's the promise of AI-driven Dockerization. The core idea is simple yet powerful. Instead of relying solely on human expertise to write Docker files, we leverage generative AI to analyze your project, understand its dependencies, and infer the most efficient and secure ways to containerize it. This means moving beyond generic Docker file templates. An AI can suggest or even directly generate Docker files that are custom-tailored for your specific Java application, incorporating best practices like multi-stage builds, lean base images, non-root user execution, and intelligent layer caching. It's about bringing intelligence directly into your build process, ensuring consistency and optimization across your entire microservice ecosystem, leading to significant gains in development velocity and operational efficiency. To illustrate this transformative concept, we've put together a demonstration project called AI-OptiDoc-Java. This project isn't just theory, it provides a tangible blueprint of how AI-driven Dockerization can work. It comprises several key components that work in concert. First, a simple yet representative Java Spring Boot microservice, which serves as our application to be containerized. Second, a simulated AI recommendation script, written in Python, which stands in for a real Gen AI tool. This script's purpose is to analyze the Java project characteristics and generate an optimized Docker file. Third, the resulting Dockerfile.recommended file itself, showcasing the actual optimizations. And finally, a local build script and a GitLab CI/CD pipeline configuration, demonstrating how this entire AI-driven process can be seamlessly integrated into your automated deployment workflow. Each component plays a vital role in showcasing the end-to-end acceleration of Java microservice deployment. Let's start by looking at our sample Java Spring Boot microservice. For this demonstration, we've kept it intentionally simple: a basic Hello World REST API. It's built with Spring Boot and Maven, which are standard choices for enterprise Java development. The application exposes a single /API/hello endpoint that returns a simple greeting. While the code itself is minimal, its structure and dependencies are typical of a real-world Spring Boot application. This simplicity allows us to focus on the Dockerization aspect without getting bogged down in complex business logic. The pom.xml handles the dependencies, including Spring Boot Starter Web for our REST capabilities. This simple setup serves as the perfect canvas to highlight how even a straightforward application can benefit immensely from an optimized Docker file, leading to smaller, faster, and more secure deployments, which is precisely what we aim to achieve with our AI-driven approach. The true innovation here lies in the brain of our system, the recommend_dockerfile.py script. In a real-world scenario, this Python script would interact with a sophisticated generative AI service, like a large language model. It would feed the AI various metadata about your Java project, perhaps the language, framework, specific dependencies, and even your desired optimization goals, like minimizing image size or prioritizing build speed. The AI would then process this information, cross-referencing it with an immense knowledge base of Docker best practices, security guidelines, and Java application deployment patterns. For our demonstration, recommend_dockerfile.py simulates this process. It contains predefined logic to output a highly optimized Docker file, showcasing the kind of intelligent recommendations a real AI would provide, highlighting multi-stage builds, strategic layer caching, and other crucial optimizations. This script is the bridge between your code and an intelligently designed container image. The output of our AI simulation, the dockerfile.recommended, is where the rubber meets the road. This isn't just any Docker file, it's a meticulously crafted artifact designed for maximum efficiency. It starts with a multi-stage build, a critical technique for Java applications. The first stage, named build, uses a JDK image to compile your application. Crucially, it copies pom.xml separately before copying the rest of the source code. This intelligent layering leverages Docker's build cache. If your Maven dependencies haven't changed, Docker won't re-download them, significantly speeding up subsequent builds. The second stage, final, uses a much smaller JRE base image, stripping away all the build tools, resulting in a significantly smaller final image. Furthermore, it incorporates security best practices by running the application as a non-root user and includes optimized JVM arguments, XMS, XMX, XX, plus use container support, essential for efficient memory management within containerized environments. These subtle yet powerful optimizations are precisely what an AI can consistently deliver, often surpassing what a human might manually achieve. Let's walk through how this all comes together locally using our build.sh script. This script orchestrates the entire process, mimicking a simplified CI/CD pipeline on your local machine. First, it invokes mvn clean package, skip tests to compile our Java microservice and package it into an executable JR file. This is the standard Java build step. Next, and this is the crucial AI-driven part, it executes Python 3 recommend_dockerfile.py. This is where our simulated GenAI analyzes the project and generates the dockerfile.recommended in your project root. Finally, it calls docker build .tai_optdoc_java, latest, f_dockerfile.recommended. This command instructs Docker to build an image named ai_optdoc_java, latest using the AI-generated Docker file. Once the image is built, you can run it with docker run p8080:8080 ai_optdoc_java, latest and verify its functionality by accessing http://localhost 8080/API/hello. This local execution flow perfectly demonstrates the integration of AI into your development cycle, showing the immediate impact of the optimized Docker file. The real power of AI-driven Dockerization shines when integrated into your continuous integration/continuous delivery (CI/CD) pipeline. Imagine every code commit automatically triggering an intelligent Docker file generation process. Our .gitlab.ci.yml file provides a practical example of this. The pipeline is structured into distinct stages: build Java, AI recommend Dockerfile, and Docker build push. The build Java stage compiles your Java application using Maven, just as you would normally. Critically, the AI recommend Dockerfile stage, running a Python environment, executes our recommend_dockerfile.py script. This script dynamically generates the dockerfile.recommended based on the latest project state. Finally, the Docker build push stage then uses this newly generated and optimized Dockerfile.recommended to build the Docker image and push it to your container registry.